Hey, it's day 2, unit 15. We're talking about probability and percentiles using a normal curve. It's saying Kevin's math grades are steadily improving. His test average is now an 88. Yay, Kevin. The mean of all students' test scores in the class is 91, standard deviation of 3. It says assume test scores in the class follow a normal distribution. That's actually something that's pretty important. You can't assume something's normally distributed, so any question with it should always say it follows a normal distribution. Kevin's z-score, right? A little review. Z-score is his actual score, 88, minus the mean. So the mean was the 91, and then here was his 88, divided by the standard deviation. Right, so you get -3 over 3. We get a z-score of -1. So that's a nice, pretty z-score. So it says, does the z-score suggest that Kevin did better or worse than the average math student? Well, worse, because if it's negative isn't always bad, but what negative does mean is it means you're below the mean. So in terms of grades, yeah, below the mean's not good. All right, on the curve, it says label the mean and the standard deviation of the class scores and put a star, on Kevin's scores. All right, so the mean is always represented by the 0. So it's dead center here. So that is the 91, right? Kevin is 1 standard deviation below the mean, which makes sense because if you go 3 points below, there's 88. So we can put a little star right there. There's Kevin, all right? And then if you want, you could go 3 above and say there's 94 and 3 above that. So if you're 1 standard deviation above, you'd be 3 points. 2 standard deviations above, it'd be 97 and so on. All right, which kind of makes sense because 3 standard deviations above, that would be about 100, which should, it says technically there's 0.1 above here, but this is approximate. So when it says what percent of students are doing better than Kevin, all right, you can add up everybody above this, right? So you can add all percentages above Kevin's, score. Add everybody from here over. So all of this, okay? That means we would be adding the 15% plus 19.1, and then keep going, another 19.1, and so on. All right, now something you might realize, dead center to the right is 50%, to the left is 50%. So you could even say, all right, let's forget that, do 15 plus 19.1 plus 50%, and that would cover it right there. All right? So if we grab our calculator, if we do 15 plus 19.1 plus the 50, 84.1. So that's the percentage of students that did better than he did, all right? That's a lot of students right there. When it says Kevin is doing better than what percentage of the students, well, in that case, you could add up everybody to the left. So you could add all the percents below Kevin's score, which means to the left, whereas up here it was to the right, right? Or you could do 100 minus the values above. So there's a lot of ways to do this. Otherwise, you can add up the 0.1, 0.5, 1.7, and so on. I'm going to go the faster route and go 100 minus 84.1. If we do 100 minus 84.1, that'll leave us with 15.9. It says shade the percentile or the area to the left of Kevin's grade. That area is the percentile. All right, well, I kind of used my yellow, so I'll use my blue for this. So this, everything below Kevin's score, that's the percentile, right? So when you guys have taken like SATs or PSATs and it tells you what percentile you're in, this means I'll round it and say he's in about the 16th percentile. That literally means, all right, you did better than about 16%. And 84% did better than you did. Of percentile, right, is the percent of people that lie to the left or below. So I'm going to kind of say it both ways, left or below, right, of that value. So something to keep in mind. If you're all the way to the left, you would literally be at the 0% or 0 percentile, right? If you're all the way to the right, that would be at 100%. When it says here, you took the SATs, you did not receive your numeric score. Whoops, sorry, off the screen there. For the math portion, testing service only stated that you scored in the 97.7 percentile. See right there, I'd be like, done, thank you, I'm awesome. The mean score is 525, standard deviation of 100. So what score did you get? Okay, so they're basically asking you to figure out where in this chart is the 97.7th percentile. Couple ways that you could do that. I could start at the left and I could count all the way up until I hit 97.7, or I can start at the right and work my way down. So we said all the way to the right is 100%. So what I mean by work your way down, let's take 100% and let's subtract the 0.1. Oops, except for I added 100% minus 0.1. Woohoo, there we go. All right, so right here, if you're on the 3, you'd be at the 99.9 percentile. Let's subtract another 0.5. Right here at the 2.5, you'd be at the 99.4, and I can keep playing this game. Let's subtract 1.7. So right here, if I was at the 2, I would be at the 97.7 percentile. That's what I care about. So at this point right here, that's the 97.7th percentile, which sometimes I do cheat and write the percent sign and then "ile" next to it. So just so I don't confuse you. All right. That means if you're here, if you're 2 standard deviations above the mean, because that's what this 2 represents. This is 2 standard deviations above the mean. That means that when the data is normally distributed, like it is for an SAT, that you would have done better than almost 98% of the kids that took it. All right. If we lay out the scores, let's take a look at like what they gave us. They said 525 is the mean, so that goes dead center. So 525 is right here. Each standard deviation is 100. So if I go 1 standard deviation above, that's a score of 625. If you go 2 standard deviations above, that would be like getting a score of 725. So when it says, what score did you get? Well, there you go. All right. You would have to take the mean. Oops, let me slide down here a little bit. You'd take the mean, and we're adding 2 standard deviations to it. Or if I use my symbols, you'd take X bar and add on 2 of those sigmas. Right? So 525 plus 2 of those standard deviations gives you a score of 725. Ta-da! It says your friend is really bad at math. Oh, that's unfortunate. She was in the 6.7th percentile. What score did she get? Okay, 6.7 percentile. Start on the left side and keep adding up until you hit 6.7. So if we do 0.1 plus 0.5, you know that's not enough. Plus 1.7, still not enough. Oops, I'm so sorry. I'm adding and I'm off the screen there. Plus 4.4. There we go. That's it. So I want to include this chunk, and the 4.7. So I'm right here, which means to be at the 6.7 percentile, you have to be 1.5 standard deviations below the mean. All right. There's the 6.7th, and I'll use my abbreviation there, percentile. There we go. Okay. So when it says, what score did she get? Well, you have to take the mean and then subtract 1.5 standard deviations from it. So that's how you use those z-scores. That's what they stand for. So let me slide this up just a little. So that means we're going to take the mean and subtract 1.5 standard deviations. Or I'm going to take X bar and subtract 1.5 sigmas, like that. All right, let's plug in the numbers. 525 is the mean. Subtract 1.5 standard deviations at 100 each. Well, that's fairly simple math. That would just be minus 150. And when you subtract 150, that means she got a 375 on the math portion. 4. It says, what if your score doesn't fall on a whole or a half standard deviation? Because the ones that we just did were 2 above, 1.5 below. Those are nice and pretty. right? In that case, your z-scores, we can use the calculator. So the calculator will do it nicely for us, right? So let's do it with this particular example. It says the top swimmer at FHS swims the 50-meter backstroke on average in 39.7 seconds with a standard deviation of 2.3 seconds. Now, how would they know this? They would have had to put like all their times in and do like one variable stats, and they'd get that stuff. So you can actually calculate these things. It says, assuming the situation follows a normal distribution. So there it is. They're telling you that that's happening. Find the probability to the nearest thousandth that she swims her next race between 37 seconds and 44 seconds. So it says, sketch your normal curve with the mean at the center, put the 37 and the 44 on the graph, and shade the area you're trying to find. All right. If we draw our normal curve, do your best. Sometimes they come out a little lumpy. It's okay. We won't judge. All right. So on average, 39.7 seconds. So dead center is the 39.7, right? And then it's saying, what's the chance that she swims between 37 seconds and 44? So 37 would be below it. 44 would be somewhere above it. It doesn't have to be drawn perfectly to scale, but I want you to draw vertical lines, and we're going to shade off that area in between here. Right? Because when we ask what's the probability, all of this together we know adds up to 100%, or you can think about it in probability, it would add to 1. So we want to figure out what's the percentage, right, that lies between those two times. Or as a quick reminder, you take the actual score. So I'm going to start with the 37, subtract the mean, divide by the standard deviation, which they told us was 2.3 back up here. Right? And then we'll do the same thing for the second one. You'll do 44 minus the mean of 39.7 divided by the standard deviation. So it's just going to tell us how far above and below those values are from the mean. So if we do 37 minus 39.7 divide by 2.3, the first one comes out to be negative 1.174 if we round to the nearest thousandth. And then the second one, if you calculate it, comes out to be 1.870. So what that actually means is that that lower swim time is just over 1 standard deviation below the mean. The upper one is like 1.8, 1.9 standard deviations above the mean. And now because they're talking about times, the low one is actually the better one. So this one is going to be the lower value that we need. This one is going to be the upper value. All right. So on your graphing calculator, I'm going to slide this up and I'll show you as I go. It says determine the values that fall in between them. And so what we're going to do is we're going to go to second, VARS, and then normal CDF, because that's what this is. It's a normal curve. The CDF stands for cumulative density function. Don't worry too much about that, but go to second, and then VARS is right. I don't think you can see my finger there. VARS right there. So second, VARS. And then it's not the first one. The first one's PDF. We want CDF. All right. So it's the second one there. Right. And now there might be numbers in there from before. There might not. That's okay. It's going to be the negative 1.174. So type that in here. The upper was the 1.870 because obviously it needs to go low to high or this isn't going to make sense. And now for this part, that little, it looks like a U, but it's a mu, right? That is going to be the mean, which the mean is 0. The standard deviation is 1. Right? So we're going to type that in as 0 and 1, which they might have been defaulted to 0 and 1 on your calculator anyways, which is fine. All right. Go ahead, just hit paste, which for mine takes me back to the home screen, and then hit enter one more time. Now, for any of you, if you have an older calculator, you have to put them in a particular order. You got to do lower, then upper, mean, sigma, and you have to put commas in between. Yes, there is a comma button on your calculator. It is right there above the 7. So if you have one of like the chunkier old calculators, you're just going to do it in that order. So practice it. Make sure you know how to do this, right? And then what it comes out as is 0.849. And so what that means, that's the probability that she would swim between those two times, right? So as a little reminder, the mu, that's the mean. The sigma, that's your standard deviation. So when you bring it back to that normal curve, the mean is always the 0. The standard deviation is always the 1. So that's where it's coming from. All right, so you're going to keep that 0 and keep that 1. Find the probability to the nearest thousandth that the swimmer's time is more than 45 seconds. So like she gets a cramp and like swims a really stinky time or something. So draw your chart first. All right, dead center, that's the 39.7. And it's saying more than 45 seconds. 45 seconds would be way up here. If we're talking about more than that time, that means it would be higher than that or above it. So we're talking about this part right here. All right. In a case like this, you still want to find the z-score. So we just need the z-score for the 45. So we do 45 minus the mean of 39.7 divided by 2.3. That comes out to be 2.304-ish, right? What that is, when you look at this area, this is the lower. Up here would be the upper when you're reading it from left to right. So, well, what the heck is the upper? Well, yeah, I know that the normal curve really goes from like -3 to +3, but we kind of treat it like it's infinity. Upper value, to kind of let it approximate infinity, we're going to type it in as 1 times 10 to the 99th power. And we get to use that little caret key to do it. So on your calculator, here's how we're going to do this again. We're going to go to second, vars, and we're going to do a normal CDF. And I'll run you through that one more time. You're going to give it the lower bound, the upper bound, the mean, and the standard deviation. Now, the cool thing is mean and standard deviation, when I use z-scores, are always going to be 0 and 1. Now we're going to use the z-score for the lower. That's the 2.304. And for the upper, we're going to use that approximation of infinity. So 1 times 10 to the 99th power. All right, let's try it. So over here, I'm going to go see if I can get all this on the screen so you guys can see. There we go. We're going to go to second, vars, choose normal CDF. So that's 2. And now I'm going to type right over. So 2.304 is the lower bound. The upper bound, 1 times 10, raise it to the 99th power. So use your caret key, and then keep the 0 and 1. And then paste it. Hit enter, and the probability comes out as 0.0106 and so on. So they're saying, all right, what's the chances that she's going to swim more than 45 seconds? It's like a 1% chance, because she's awesome. And it doesn't make sense that she would swim such a slow time unless she got like a cramp or something crazy like that. So 0.011 to the nearest thousandth would be the answer there. Guess that here, when it says use the same mean and standard deviation and so on, find the probability that the swimmer's time is less than 39 seconds, means that we'd be using the left end of the curve here. So if here's 39.7, swimming a 39 would be like right next to that. And then anything less than, I'd be shading below. So in this case, lower bound, upper bound, the lower bound, we're going to treat like negative infinity, which means we're really going to make it -1 times 10 to the 99th power. We're going to try to make that like a super, super small number. And then the upper bound would be the 39. So lower would go here, upper would go